Hi everybody, myself Dinesh. Welcome to BYJU'S Exam Prep, India's most comprehensive exam preparation platform. So in yesterday's session we have talked about pulse code modulation. So I've talked about sampling, quantization and encoding, right? So we were discussing about quantization in detail. So we are supposed to discuss few more things about quantization. We have to calculate quantization noise power and SQRF. So I'm going to teach you first about how to calculate quantization noise power and signal to quantization noise ratio. I'm going to cover. So listen to this concept very carefully, because whatever concept I'm going to teach you, I'm going to give you an idea of how to solve the problems based on tough problems based on quantization. Right. So I'll cover all models. Don't worry. So this is my profile. So I have 10 plus years of experience. I've done my masters from IIT Madras with specialization communication systems. So my subjects of expertise is communication systems and signals and systems. So I worked for the best top institutes in the country for the last 10 years. So one more thing is, this is my Telegram group. If you wish to ask me any doubts based on these subjects, or if you wish to ask me anything else, whichever you feel like I can help you with, so you can contact me on this Telegram group. Right. So what is the agenda of today's session? So what I'll do is, first I'll give you the answers for homework questions quickly, and then after that I'll cover quantization noise power and SQRF calculation first, and after that we'll move on to today's topic, which is practicing different models of questions on pulse code modulation. So these are the questions that I've given as homework in yesterday's session. So only one student has responded with the answers. So I expect more students to respond with the answers. Right. So the first question, let me give you the answers quickly. So a signal of bandwidth 16 kilohertz is sampled. So B is given. Bandwidth B is given as 16 kilohertz. And it is sampled at 100% higher than Nyquist rate. You know what is Nyquist rate, right? Nyquist rate is always F Nyquist is equal to 2 times bandwidth. Nyquist rate is nothing but the minimum sampling rate required to sample a signal. The minimum sampling rate required, we call it as Nyquist rate, which is 2 times the bandwidth. Any sampling rate greater than Nyquist rate is okay for us to preserve quality, right? So what is the sampling rate required? It's not Nyquist rate, it is 100% higher than Nyquist rate. 100% means it's double. 100% higher means it's like 200% of Nyquist rate. So 200% of Nyquist rate means it's 2 times of Nyquist rate, F Nyquist. So which is equal to 2 times, Nyquist rate is 2B, which is equal to 4 times B. B is given 16 4s are 64 kilo. What is the unit of sampling rate? You can write it as samples per second. You can write it as samples per second, or sometimes you might find it as hertz also, because sampling rate, we also call it as sampling frequency sometimes. When we call it a sampling frequency, we can say it as 64 kilohertz. When we say sampling rate, the appropriate unit is samples per second. Right, so that is the answer. A sinusoidal signal, second question, a sinusoidal signal of bandwidth 16 kilohertz is sampled at Nyquist rate. So it is Nyquist rate. The sampling rate is same as Nyquist rate. Sampling rate need not be same as Nyquist rate. Okay, it can in the question, whatever information they give you about sampling rate, we have to take that. In this question, it was not Nyquist rate. It is 100% higher than Nyquist rate. In this question, they have given that it is Nyquist rate. One more important thing I'll tell you: whenever in any question, if they're saying that they're sampling, and they did not mention what sampling rate they are using, if they did not mention, they did not give you any hint of what kind of sampling rate they are using, you can assume that it is Nyquist rate. Whenever there is no information about what sampling rate is being used, you can assume it is Nyquist rate. Okay, right. But in this question, it is clearly given that they are using Nyquist rate. They're saying that they are using Nyquist rate. So and then they encoded using a 4-bit PCM system. 4-bit, N is 4 here, and B is 16 here. And sampling rate we know. So finally, what we want is find the bit rate of the PCM system. Bit rate RB is equal to, it is given as NFS. N is 4 here, and what is Fs? Fs is same as Nyquist rate. Nyquist rate is equal to 2 times bandwidth. And what is the bandwidth? Bandwidth in this case is 16 kilohertz. 2 into 16 kilo. So which is equal to 4 2s are 8, 16 4s are 64, into 2 is 128 kilo. Bitrate unit is bits per second. So answer is 128 kilo bits per second. Is that okay? Good evening, Marty. 32 clades. For what question is that answer? It's 64 clades, right? 16 4s are 64. It's not 32, right? Okay. Last question. Let me answer the last question. Whatever questions I've given in the homework, they are very, very simple questions. Why I've given you very simple questions is because yesterday I have not covered any problems. So whatever questions I've given is based on very basics. Okay. In today's class, we'll cover wonderful questions, and at the end of today's class, I'll give you homework also, and they will be tricky questions. Okay. You can wait for them. Okay, Marty, see this one. What is the sampling rate? It is sampled at 100% higher. 100% higher. So for example, my marks is 20 marks. Okay. If somebody says Marty got 100% higher than Dinesh marks. 100% higher means what? I got 20, you got 100% higher than me. 100% means, which is original itself, you can treat it as 100%, but the sampling rate used is 100% higher. Marty got 100% higher marks than Dinesh, which means it is 40 marks, right? It's double. Okay. Similarly, I'll ask you similar questions, okay, to make it clear. When I say 50% higher, 100% is original, 50% higher means it's like 150%, which is 1.5 times of original. Okay. 50% of original is different, 50% higher than original is different. If I say 100% of Nyquist rate means it is only Nyquist rate. I'm saying 100% higher than Nyquist rate. There is a difference between 100% higher than Nyquist rate or 100% of Nyquist rate. Okay, I hope you are getting the difference. If I say 20% higher than Nyquist rate, instead of 2, I'll put 1.2, because 20% higher, na? Nyquist rate is original. 20% higher means it's 20% higher than means it's like 1.2. Factor is 1.2. I hope you're following. Right. If it is 30% higher, then it is 1.3. The factor multiplied is 1.3. If it is 50% higher, the factor multiplied is 1.5. If it is 200% higher, then the factor multiplied is 3. Original is 100%. Original is F Nyquist. How much is higher? You increase that factor by those many times. Okay. Simple thing only, but you have to understand what is happening here. Right. In any other question also, you might be facing with this kind of sentences. You have to be careful. Right. Next, the last question. A signal taking voltages from 0 to 16 volts is applied to a 4-bit PCM system. Find the step size and maximum quantization error. So they are talking about step size. Step size formula is, we have discussed it yesterday. Voltage swing, which is, voltage swing means it's the range of voltages possible for the signal, or highest voltage minus lowest voltage, divided by number of quantization levels. Number of quantization levels, which is equal to, what is the voltage swing? They are saying voltage taken by the signal are from 0 to 16. Highest voltage is 16 minus lowest voltage is 0. Difference between them will give you voltage swing, or the range of voltages possible. Divided by number of quantization levels is, because it is a 4-bit PCM system, n is equal to 4. If n is equal to 4, number of quantization levels, m is equal to 2 to the power of n. Or the reverse relation is n equal to log m to the base 2. So which is equal to 16. The number of quantization levels that we can use is only 16, because number of bits are fixed as 4. So 16 you can substitute here. It is 1 volt. So we got step size as 1 volt. And how about maximum quantization error? Maximum quantization error is, it is half of the step size. It is half of the step size. And how much is that? 1 volt divided by 2 is 0.5 volts. The maximum error possible is 0.5 volts. Okay. Right. So these are the answers. So I hope many people got the right answers. So one person has answered correctly in the comment box. So you can see that it is 128 perfect. First question answer is correct. Second is correct. Third is also perfect. Right, wonderful. So remaining students, whoever is following this class, can take time to solve the questions and put it in the comment box, so that I'll understand that you people are getting it right. Okay, fine. So now let's talk about for the next 20 or 25 minutes, just focus, very carefully focus, because this is very, very important, very, very important and very tricky also. We can solve a lot of tricky questions with this concept. Let's start. So what are we supposed to discuss? We want to discuss quantization noise power, right? Right. So before talking to talk about quantization noise power, I'll just quickly draw the quantizer characteristics and the quantization error characteristics also, which you might have seen in your textbooks. But I'll quickly draw to convey some point. I want to convey some point, so because of that I want to draw this. If you remember yesterday's class, I have taken a signal, I have taken an example of 0 to 16 volts, right? I'll take the same thing, 0 to 16 volts, or let me take a general thing, okay? Let us take a general thing. So to draw quantization characteristics, which means input versus output characteristics, whenever somebody asks you to design a quantizer, it means once you design a quantizer, you should be able to plot the characteristics of the quantizer, which means input versus output characteristics of the quantizer. So for a quantizer, let me say the input is x and the output is y versus x characteristics. Okay. So yesterday I told you that the definition for quantization error is input x minus output y. So we should be able to plot these characteristics based on the design of quantizer. Yesterday I told you how we design the quantizer. We divide the total range into m parts. How many quantization levels are there? Those many regions. We divide the total region into multiple regions. How many regions? It is decided by the number of bits. Number of bits decided the number of quantization levels. Number of quantization levels decide the number of regions. We have to divide the total range. Okay. So for example, let me take some signal, message signal, some m of t signal, takes voltages from minus am to plus am. For example, let me say that. If you want, you can say it as minus 4 to plus 4 volts. Okay. So how about step size? Step size is equal to voltage swing is highest voltage minus lowest voltage, which is 2 am divided by number of quantization levels, or number of quantization levels, which can also be written as 2 power n. 2 power n. It can be written as m or 2 power n. Right. So if n can be any number, okay? N can be any number. But if n is very large, it will be difficult for me to plot quantizer characteristics on this board. If n is practically we take n as 8, then 256 quantization levels will be there. So 256 levels if I draw, this total class also I will not be able to draw the total characteristics, and this board also will not be sufficient. So just for the sake of drawing and to explain it clearly for you, let me take some n value, which is a smaller value. If n is small, then only quantization levels will be so that I can draw the characteristics on the board. So let me take some n as n is 3. I'm talking about a 3-bit quantizer. If n is 3, then what is m value? M value is 8. So m value is 8 means we have to divide the total region, total voltages possible in the signal into 8 parts, because I'm assuming n is 3. So the lowest voltage possible is minus am and highest voltage possible is plus am. Let's divide this total range into 8 parts. When you divide this into 8 parts, each part, the length of each part or length of each region, we call it a step size. Okay. So totally how many regions will be there? How many quantization levels are there? Those many quantization regions will be there. Okay, those many regions will be there, and each region is of length delta. So if each region is of length delta, total regions is 8 regions. So total length will be 8 delta. Correct or not? See this one? For when n equal to 3, delta is equal to 2 am divided by 2 power 3, which is 8 in this case. And 2 am is equal to 8 delta. 2 am is what? total range of voltages possible. So the total range is divided into 8 delta. This total length can be written as 8 delta. 8 delta means this part is 4 delta and this part is another 4 delta. So let me say this is delta, second point is 2 delta, and third point is 3 delta, and this one is 4 delta, correct? Because only 4 deltas are possible here and 4 deltas possible here, because total length is 8 delta. Okay, this AM we can also write it as 4 delta. Similarly on the negative side also, minus delta, minus 2 delta, minus 3 delta, and minus 4 delta. Very simple. Whatever voltages are possible for the signal, those voltages, the total range of voltages, you divide it into m parts. How many quantization levels are there? Those many parts. So we got quantization regions now. This is one quantization region, another quantization, third quantization region, fourth region, fifth region, and so on. Total 8 regions we are having. And whatever points we have selected here, whatever points we are having selected here, first point and last point and the middle point, all these points, we call them as quantization boundaries. Because they are the boundaries of regions, right? This is the first region. These 2 points are the boundaries of that region. These 2 points are boundaries of the next region. These 2 points are boundaries of the next region, and so on. We call them as quantization boundaries. They are not quantization levels. But these boundaries, we can take the midpoint of these boundaries as quantization level. So what is the midpoint of 0 and delta? It is delta by 2. When you give input as any voltage between 0 and delta, we take the quantization level as, for this quantization region, to get least error. Finally, the basic idea of designing a quantizer is to get a least amount of error possible, or average error or quantization noise power should be as less as possible. That is the basic idea of designing a quantizer. An efficient design of quantizer means we should get, on an average, for all voltages combined, on an average we should get smallest error possible. That is the intention behind designing a quantizer. That is the only thing that should be kept in mind while designing a quantizer. Right. So generally, to get the minimum possible error, we take the midpoint of each region as the quantization level. So midpoint of this region is delta by 2. When you apply any of these voltages as input to the quantizer, what is the output? The midpoint of this, which is delta by 2. So delta by 2 is the quantization level. Delta by 2 is the quantization level corresponding to this region. Next, how about this region? This region midpoint is 3 delta by 2 or 1.5 delta. Whenever you apply any voltage in this range, in this second quantization region, the output, if it is 1.5 delta, then error will be, on an average, error will be as less as possible. So for this region, the quantization level corresponding to this region is 3 delta by 2. Similarly, next region, midpoint is 5 delta by 2. Similarly, same way analysis you can do for the next region also. This is 5 delta by 2, and the next region, it is 7 delta by 2. Similarly, on the other side also we can do, for this region midpoint is minus delta by 2, that is the quantization level, and for the next region it is minus 3 delta by 2, and for the next region it is minus 5 delta by 2, and for the next region it is minus 7 delta by 2. Understand carefully. So this is the quantizer characteristics. So this way you can design a quantizer and plot the quantizer characteristics. Given an n value, you should be able to design the quantizer characteristics. There are only 8 levels. See this one? 1, 2, 3, 4, 5, 6, 7, 8. Why 8 levels? Because number of bits is 3. Number of quantization levels possible is only 8. How many values of y are possible? There are only 8 values of y possible because only 8 quantization levels are allowed, because only 3 bits are allowed. Right. So let's come to the most important point that I wanted for the discussion in today's class. That is another characteristics, which is input versus quantization error characteristics. Input versus quantization error characteristics. Okay, right. Let's draw the characteristics. Before drawing the characteristics, let me mark this delta, 2 delta, 3 delta, and 4 delta. Okay, now understand carefully. So quantization error. On y-axis it is quantization error, and quantization error is given as input minus output, x minus y. We already have y versus x characteristics. Now what we want is x minus y versus x characteristics, because we want quantization error with respect to y characteristics. Okay. Now let's understand carefully. Right. So when the input is little higher than 0, let's say 0.1 or something like that. When the input is little higher than 0, something like 0.01 or little higher than 0. When the input is little higher than 0, our input is in the first quantization region. When the input is in the first quantization region, what is the output? The output is delta by 2. When the input is anywhere in the first quantization region, the output is delta by 2. Input is just greater than 0, almost 0 you can say, but positively 0, almost 0, minus, what is the output? When the input is positive and small positive value, the output is delta by 2 of the quantizer. The output of quantizer is delta by 2. So this is almost 0 minus delta by 2 is minus delta by 2. So error is how much? Error is minus delta by 2. Next, let us, if you increase x, as you increase x in the first quantization region only, as you increase x, y will stay same. Before, in this region, in this total region, y is always delta by 2, y is fixed. But as x increases, x minus y increases because y is fixed. So this is minus delta by 2. Just after 0 it is minus delta by 2, and it increases, and at the midpoint, when the input is delta by 2, then also output is delta by 2. When the input is delta by 2, output is also delta by 2, the quantization error is 0. So as x increases, quantization error increases till delta. Just before delta, what happens? Try to understand. Just before delta, what happens? Try to understand carefully. Just before delta, this is almost delta, but just below delta. So output will be always delta by 2 in this region. Output is delta by 2. Input is almost delta. Delta minus delta by 2 is delta by 2. So maximum error possible is at the boundaries. At the quantization boundaries, we get the maximum error. At the midpoint of the quantization boundaries, we get the least error. Right. So that is how it happens. After delta, what happens? Just after delta, we come into the second region. For second region, when any voltage in the second region is given as input to quantizer, output is 3 delta by 2. When the output is 3 delta by 2, and the input is just higher than delta, this is almost delta, and this is 3 delta by 2, then the error will be 3 delta by minus delta by 2, same as the. And as x increases in this region, quantization error also increases because y is fixed at 3 delta by 2. So it will be characteristics. Same characteristics will repeat here. Similarly, from 2 delta by 2 to 3 delta, the next region also same characteristics will repeat. Next region also same characteristics will repeat. Similarly, on the other side also, same characteristics will repeat. Same characteristics will repeat. Something like this. Okay. So finally, the point I wanted to convey here is quantization error. What are the values taken by quantization error? Can anyone tell me what values are taken by quantization error? Marty, is it visible? Yes, no? Is the board visible or not? I hope you can see that it is clearly visible. Okay, fine. Right, understand carefully. Quantization error. What are the values taken by the quantization error in the first region or second region or third region or all regions? It is taking the same values. And what is the minimum value possible? Minus delta by 2. Maximum value possible is delta by 2. So the range of voltages possible for quantization error is minus delta by 2 to plus delta by 2. All voltages are possible. Correct? The voltages possible for quantization error is anywhere between minus delta by 2 to plus delta by 2. Is it going to take 0? Is it going to take minus delta by 2 or delta by 2? It can take any value in that range. Based on input voltage, it can take any value. If the input voltage is just higher than 0, it will take minus delta by 2. If the input voltage is delta by 2, it will take 0. If the input voltage is close to delta, it will take plus delta by 2. or if the input voltage is anywhere in between, the quantization error will be anywhere in between, right? So all errors are possible, from minus delta by 2 to plus delta by 2, all errors are possible. Okay, right, wonderful. Try to understand carefully. Now, can anyone tell me what is the probability of quantization error to take delta by 2? Quantization error can be delta by 2 in multiple scenarios. In what cases? When the input is just below, delta, when input is just below delta, or delta minus, I'll say, or when the input is just below 2 delta, when the input is just below 2 delta, so 2 delta minus, you can say. Similarly, when the input is just below 3 delta, and so on. Similarly, on the other side also, the plus delta by 2 is possible at this voltage, at this voltage, at this voltage, at this voltage, at this voltage. Totally 8 places, 8 values of x are responsible for the same error delta by 2. Okay, which means the probabilities of x will influence the probability of quantization error. I've only talked about quantization error, the probability of quantization error to take delta by 2. Similarly, you can understand for delta by 4, delta by 3, delta by 6. Okay, for other quantization errors also, you can understand the probability that error will take that voltage. We can similarly understand it. The point I want to make here is, probability of quantization error taking a certain voltage, is it dependent on probability of input voltages? Yes, no? It is dependent on probability of input voltages, right? Probability of input voltages are deciding the probability of quantization error voltages. Okay, so if x is uniform, which means x takes all values with equal probability. If x takes all voltages with equal probability, if x is uniform, having uniform PDF, then quantization error, will it also be uniform? Because all x voltages are, if they are uniform, then quantization error is because of x voltages only. So if x is uniform, definitely quantization error also will be uniform. That is the easiest case to understand. Okay, so quantization error will have a uniform PDF only if x is also having uniform PDF. Correct or not? See this one, if you are not understanding. All voltages from 0 to delta, if they are having same probability. Let's understand, instead of total region, let's understand only this region. If 0 to delta, if x is taking 0 to delta with same probability, every value from 0 to delta, every x value from 0 to delta is responsible for error voltages from minus delta by 2 to plus delta by 2. Correct or not? In this region, what is the quantization error? It is x minus delta by 2. No? In this region, it is x minus delta by 2. Quantization error is, in this region, what is the quantization error? It is x minus 3 delta by 2. In this region, what is the quantization error? It is x minus 5 delta by 2, and so on. It's very clear now. In every region, if you observe, quantization error is dependent on x, and x is a input signal voltage, and input signal voltage practically are all random variables only. If x is random, quantization error is also random. If x is uniform, quantization error also will be uniform. Correct or not? If x is uniform, quantization error also will be uniform. If x is having some other PDF, then quantization error also will have different PDF, right? Things will become complicated. Other than uniform PDF, things will be complicated. So if x is uniform, quantization error will be uniform, things will become very simplified. If x is given as having PDF other than uniform PDF, then you have to analyze carefully. How to analyze? I'll discuss that in the next slides. So those are the trickiest questions possible. When they give you random variable x with some PDF and they ask you to find the quantization noise power or the SQRF, that will be the trickiest question possible in quantization. So I'll give you a very good idea about how to deal with those models. Understand carefully now. So the finally, the point I want to make in this slide is quantization error, probability of what are the voltages taken by quantization error, and the probability of quantization error voltages or the PDF of quantization error is dependent on PDF of x. That is the point I want to make in this slide. Right, let's move on to the next slide. Quantization noise power. Quantization noise power. So quantization error, what is this? This is error voltage, no? This is error voltage. If you want to power, what should we do? QE square, generally if you square the voltage, you will get power. But is QE random or deterministic? We know QE. Do you know what value of voltage QE takes? Quantization error voltage. What exact voltage does it take? Do we know that? We don't know, right? It can take any voltage from minus delta by 2 to plus delta by 2. We don't know what exact voltage it takes, which means quantization error is random. And in the previous slide also we have seen quantization error, we have written it as x minus delta by 2, x minus 3 delta by 2. In different regions we have written differently. Okay. If x is random, since quantization error is dependent on x, if x is random, quantization error also is random. For a random signal or for a random variable, how do you find the power? If you want to find the power or mean square value, if you want to find the power, you have to find the mean square value. For a random signal, how do you find the mean square value? You find it as, it's not a QE square. If it is a constant value, if you square it, you will get the power. But this is not a constant value, it's a random variable. So for any random signal or any random variable, what you can do? You can apply expectation. Expectation means it's average. QE square means what are the voltages possible for QE square? Anywhere from minus delta by 2 whole square to plus delta by 2 whole square. There are a lot of range of voltages, or a lot of range of powers are possible for quantization error. But we don't want the range of powers possible. We want the average power. So to average, we use a mathematical thing called expectation. So this will give you mean of, expectation means mean. We are using the squared value. We are trying to find the mean of the squared value of quantization error. So mean square value will give you average power, you can say, or power, you can say. Power or average power. Generally we are interested only in average power. So when somebody says power, okay, they are talking about average power only. By default they are talking about average power. Right. So what should we do? If I want to find quantization noise power, which means quantization errors power, how do we find it? Expectation of QE square. Quantization noise we are calling. Sir, it is quantization error. No, why are we calling it as noise? It's okay. Noise means something, anything unwanted, we call it as noise. So here quantization error is also an unwanted thing. So this unwanted thing we can call it as noise. Quantization error we can also call it as quantization noise. This is nowhere related to additive white Gaussian noise that is added at the receiver. This is nowhere related to that. Quantization noise is different. That additive white Gaussian noise or a thermal noise, those are different things altogether. Right. So this quantization noise is because of quantization error. So quantization error voltage is power if you want to find. Always, whenever somebody says quantization noise power, this is what we have to find. Okay. Right. Now let me talk about some basic case here. Since quantization error voltage is a random variable, for a random variable can we plot PDF? Yes, we can plot. So let us assume, do we know the PDF of quantization error? We don't know, because quantization error PDF depends on the PDF of random variable x. Okay, input to the quantizer, whatever PDF it has, quantization error also will have the same PDF. Right. So quantization error, it takes voltages from minus delta by 2 to plus delta by 2. Correct? We know that much. Quantization error voltages range from minus delta by 2 to plus delta by 2. What is the shape of the PDF? It can be any shape. That shape is decided by the shape of x, PDF shape of x, right? Let us talk about the basic case, which is if x is uniform, then quantization error also will be uniform. Correct? So let us talk about that case. If x is uniform, quantization error also will be uniform, which means it will have a rectangular shaped PDF. What should be the height? So that this will be the PDF of quantization error. The height should be, the total area should be 1 because this is PDF. Height should be 1 by delta. Then only the area will be 1. Okay, I hope you're following. Understand carefully. This is very, very important concept and tricky concept also. You have to follow very carefully. Right. Under what assumptions we are doing this? If x is uniform, or if they did not give any information about x, if x is uniform, then definitely quantization error also will be uniform. Uniform means it will have uniform PDF. That is what I mean by uniform. Okay, if X is having uniform PDF, then quantization error also will have exactly uniform PDF. Will also have exactly uniform PDF. Okay. Now, what if X is information is not given? If there is no information given about X regarding the probability density function of X, if they have not given, then also you can assume, if it is not given, we don't know what is the PDF of quantization error, but you can assume quantization error as uniform. Try to understand. Many problem models will be covered in whatever I'm going to discuss in this slide and the next slide. Very, very important. When X is given as uniform, very clearly, without any doubt, quantization error is also having uniform PDF. You can plot the PDF like this. When there is no information given about X, or if they have given X as some deterministic signal, if X is given as deterministic signal, or if there is no information about X, then also you can assume that quantization error is uniform. When should we assume, when should we take quantization error as having uniform PDF? When X is given as uniform or no information about X, or X is some kind of deterministic signal like sinusoidal signal, A cos omega naught t or A sin omega naught t kind of signal. This kind of signal also you can assume quantization error as having uniform PDF. Why am I talking about quantization error being uniform? Because many questions will be based on, many questions or many, you can say intermediate level, easy to intermediate level questions are based on quantization error having uniform PDF. Okay, I'm talking about all possible cases here. Now, what if quantization error is having uniform PDF? Okay, I have given there is some information given out about X. Based on that, we can understand some information about QE, which is uniform PDF. So what if QE is having uniform PDF? We can find quantization noise power very easily, and that is given by integration of QE square. Expectation of QE square formula, we can write it as integration of QE square. Since when we are doing expectation, we have to multiply the PDF. If X is the random variable, we'll say it as integration of X square into fx of X. Instead of X, we are having QE as the variable here, dQE. So limits from minus infinity to plus infinity. You can substitute the values. QE square into FQE of QE is 1 by delta into dQE minus delta by 2 to plus delta by 2. Only in the range from minus delta by 2 plus delta by 2, this has an equation of 1 by delta. In the remaining region, it has an equation of 0. So integrate this, you will be getting a answer of del square by 12. Understood? Quantization noise power is del square by 12. Under what condition? When quantization error is having uniform PDF. When does quantization error has uniform PDF? Under these conditions. So whenever question, information given about X is like this, you can directly say that quantization noise power is del square by 12. When there is no information also, you can say take the quantization noise power as del square by 12. But when information given about X is anything other than these three, or X is having some other PDF other than uniform, then problems should be dealt differently. How do we deal it? We'll talk about that. Okay, I'll talk about that also. But now you have understood this part, right? Quantization noise power, uniform case. Now we'll talk about non-uniform case also. You have to focus very carefully because this is the toughest part. Quantization noise power is equal to, it is expectation of QE square. Whenever X is given as non-uniform PDF, then things will become complicated. Okay. So because things will become complicated, what we should do is, I'll tell you a simple procedure here. Expectation of X minus QE, we know quantization error is given as X minus Y. I'm substituting that. But X is a random variable, Y is also a random variable. Finding expectation of two random variables will become complicated. You have to have second order PDF, which we don't have, which we can't find also. The second order PDF of X and Y. Okay, Y PDF we can find, X PDF will be given in the problem, but a combination PDF fxy of X comma Y, that is not possible to find. Okay, if somebody gives us the second order PDF, we can take it and use it, but from the first order PDF, we can't find the second order PDF. So without second order PDF, if the second order PDF is given, we can find this very easily. But since second order PDF is not available, what we can do is, let us convert this into single random variable case. How? it is expectation of x minus. See the previous slides? Just let us go back to the previous slides. What is the equation of quantization error in the first region? It is only x minus delta by 2. What is the equation of quantization error in the second region? X minus 3 delta by 2. See the equation, is it a single random variable equation or not? Basic equation is x minus y. But if you deal it in individual regions separately, when you are dealing individual regions separately, then it is a single random variable equation which can be easily dealt. If you want to find the integration of this, you just need the PDF of only x. You don't need the PDF of y. If you're trying to integrate this total thing, then you need the PDF of joint PDF of x and y. But when you're integrating this part or this one, we only need the integration of x. So we're trying to simplify this problem. Whenever x is given as non-uniform PDF, then we have to deal with it in this manner. Yes. See this one? What is the equation? It is x minus delta by 2, right? It is x minus delta by 2 whole square in the first region. In the first region, x minus y, in place of y we can replace it with delta by 2. In the second region, what is that? In the second region we can write it as, because inside this expectation we are trying to integrate from minus infinity to plus infinity, which means we are covering all regions. Integration limits, we can divide it into 8 parts now. In the previous example also, integration we have to do from integration of x minus y whole square we have to do. That integration, instead of integrating for total limits, let's integrate it for each region. So let's integrate it for this region, next this region, next this region, by integrating in that way. So totally 8 regions we'll get. So those 8 regions, do the integration separately. If you're doing that way, then what happens is y becomes a constant. Y is a constant in each region. Overall y is not constant, but in each region y is constant. We're going to take advantage of that. Y being constant in each region, we're going to take advantage of that. So in the first region, this is the equation. In the second region, it is 3 delta by 2 whole square, plus in the third region, and so on. Sir, we have to do 8 integrations? Not required, because on the left hand side and the right hand side you are having a symmetry. So if you do the integrations only for the right hand side, which means 4 integrations, that is sufficient. Okay, you can use this same procedure for when x is uniform also. You can use the same procedure, you'll get the same answer. But when x is uniform, we clearly know that QE is also uniform, so that's why there is no need to go with this complicated procedure. Go with this complicated procedure only if this is not a complicated procedure anymore. Before I have discussed this solution, it was definitely a complicated question if x is having a non-uniform PDF. But just use this procedure. If you know this procedure, if you know this technique, then it becomes an easy question. Now it's no more a difficult question. Okay, when x is given as non-uniform other than these 3, then deal the problem in this way. You'll get the answers very quickly. Okay, any confusion, just go through this part of the lecture again. I've explained everything in very clearly. So if there is still confusion, because this is tricky concept, there might be some confusions also for some of you. If at all, if there is some confusion, just go through that part of the lecture which you are not comfortable again. Then it will become clear. Okay, so this is how we are going to deal with the problem. So, sir, shall we take an example? Yes, definitely we'll take an example. We are going to do some problems. When we do some problems, then definitely we'll apply this procedure. In this class only, we'll apply this procedure. Right. Right. So since we got quantization noise power, how to find signal to quantization noise ratio? Signal to quantization noise ratio. Signal to quantization noise ratio. What ratio is it? It's not voltage ratio, it is power ratio. It is signal power divided by quantization noise power. We already have discussed how to find quantization noise power. Okay. Signal power, can we find it? If information is given about signal, we can find the signal power. If it is a deterministic signal like sinusoidal signal or a triangle signal, or if it is some kind of deterministic signal, we know how to find the power very easily, right? If it is a cos omega naught t kind of signal, power is a square by 2. If it is any signal is given as deterministic signal, we know how to find the power. For random signals also we know how to find the power. How to find the power for random signals? If x is a random variable, how to find the power? Find the mean square value which will give the power. Power is always the mean square value. How do we find it? Expectation of the signal whole square. Expectation of x square will give you the signal power if signal is random. If signal is deterministic, you know how to find the power. So finally, you definitely know how to find the signal power, whether it is random signal or a deterministic signal. And how to find the quantization noise power? As in the previous slide, we have discussed everything in detail. If x is uniform, or if there is no information about x, or if x is a deterministic signal, in all these three cases, we can assume quantization error as uniform. If quantization error is assumed as uniform, we know what is quantization noise power, which is del square by 12. If x is a non-uniform PDF, then answer the quantization noise power is not del square by 12. It is something different. So what should we do? We have discussed the procedure in the previous slide. You have to follow that procedure to find the quantization noise power. Find the signal power, find the quantization noise power, just divide them, you'll get SQNR. Tricky questions based on quantization. The tricky questions based on quantization are quantization noise power and SQNR. Okay. So they become tricky if they are giving the PDF of the signal. There can be some easy questions also framed, but they have framed some tricky questions in the past previous year question papers based on quantization. Right. So I hope you got the idea of how to find SQNR. So I'll take one special case. Let's find SQNR of one special case. If question given in the exam is different from this case, whatever case I'm talking about, then you have to solve it separately. So whatever procedure we're going to follow now, the same procedure you can follow to find signal power and quantization noise power separately, and then find SQNR. Simple. You can find this, and divide it. But in the special case also, I'm going to do the same thing. But I'm going to assume the signal. If you want to find signal power, you have to assume some signal. No? In the exam, in the question, they'll give you some signal. They'll give you some information about signal. You can find the signal power. Okay. For now, to have some formula, I have to take some signal. No? So our favorite signal is a sinusoidal signal. Let's take a sinusoidal signal, a cos omega t, omega mt, or am cos omega mt, right? So if you take this, since it is a deterministic signal, what did it tell you about quantization error? We can assume it as uniform. We can assume it as uniform. This implies what is quantization noise power? When we assume message signal as a sinusoidal signal or any deterministic signal, we can assume quantization error to be uniform, and quantization error noise power is del square by 12. One part is clear. Next, how about signal power? Signal power is also very easy, no? So that's why I'm directly writing it. Signal power is how much? Am square divided by 2. Divided by, what is the quantization noise power? Del square by 12, which is equal to Am square by 12 divided by, what is the del value? Del is, how much is the del value? It is voltage swing. What is the voltage swing of this signal? Highest voltage possible is plus Am, lowest voltage possible is minus Am. So it is 2 Am is the voltage swing. The range of voltage possible is 2 Am divided by 2 to the power of n. So this is delta. Let us substitute it here. 2 Am divided by 2 to the power of n whole square divided by 12. You can cancel this Am square, and it will become, so this 2 square cancelled with the 12, it will become 3, and this 2 into the denominator. And what is left? 2 power n whole square is 2 power 2n. That will come to the numerator. It becomes 2 power 3 by 2 into 2 to the power 2n. Okay. So which also can be written as 3 by 2 times 4 to the power of n. And since we are talking about, when we talk about powers or power ratios, we are comfortable with dB scale. So if you apply dB scale, what should we apply? Should we apply 10 log or 20 log? When we are dealing with second order terms, apply 10 log. When we are dealing with first order terms like voltage or current, apply 20 log. Since SQNR is a ratio of powers, power is a second order quantity. Power or energy is a second order quantity. Whenever we are dealing with power or energy, because they are second order quantities, apply 10 log. Whenever you want to convert it to logarithmic scale, apply 10 log. Right, apply 10 log to this. 10 log 3 by 2 into 4 to the power of n. So 10 log 3 by 2, you will get something like 1.8 plus 10 log 4 power n is 6n. So the answer is 6n plus 1.8 dB. As you increase 1 bit, as you increase n by 1 bit extra, the SQNR increases by 6 dB. Or as n increases by 1 bit, SQNR increases by 4 times. 4 times is same as increasing by 6 dB. 4 times or 6 dB both are same. 4 times in normal scale is same as 6 dB in dB scale. Right? We got SQNR for one special case. And what is that case? If m of t is sinusoidal, that is when this answer is applicable. If they have given m of t as sinusoidal, or if there is no information about message, in both these cases, you can say the answer for SQNR as 6n plus 1.8. Okay, fine. So let's, if m of t is not sinusoidal, if it is something else, what if it is some other signal? If some other signal, but the quantization error is uniform. Some other signal means it can be some other shaped signal other than sinusoidal signal. Then also we assume quantization error is uniform. So this is del square by 12. But here the factor will change. Instead of am square by 2, it will be some other factor, am square by 3 if it is triangle signal. If it is some other shaped, it is am square by some other constant. If that constant changes, only this part changes. Na? This 2 power 2n part will not change. No? This 2 power 2n part will not change. So this 4 power n part will not change. This 6n part will not change. Only this constant part or this constant part will change. So always this 6n relation or 4 power n relation is always consistent. For some other signals also, that relation is consistent. If m of t is non-uniform, then this is not applicable. Okay, if they have clearly given m of t is having a PDF other than uniform PDF, something like some triangle PDF or some other complicated shape PDF, then this answer is not applicable. If m of t is sinusoidal, or if m of t is uniform, or if m of t is any other deterministic signal, here 4 power n factor will be there, 6n factor will be there. The constants might change for some other signals, but 6n and 4 power n factor will be same. Okay, which means they can frame wonderful questions based on this simple relation. They'll ask you questions like this. If number of bits are increased by 1 bit, they don't need to give the information that message is sinusoidal. For some other signals also, that 6n factor and 4 power n relation is consistent. So they'll ask questions like this. If n is increased by 1 bit, how many times SQNR increases? 4 times. How many times SQNR changes? 4 times. How many dB it will change? 6 dB it will increase. Right? Well, how about same way? Let me ask you one more. What if n changes by 2 bits? If n changes by 2 bits, n changes by 2 factor, 4 power 2 is 16. SQNR changes by 16 times. Or dB, in dB scale it changes by 12 dB. Right? So questions can be asked based on this relation. Some good questions, decent questions can be framed on based on, intermediate level questions you can say, based on this relation. So we can blindly use this formula if there is no information in the question, proper information in the question, or if they have clearly given that they are using sinusoidal signal. If m of t is non-uniform, which is a rare case, they talk about m of t being a non-uniform PDF, m of t having non-uniform PDF case, that is a complicated case. Very rarely they ask questions about that, but that will be the tough question. If they have given m of t as having a non-uniform PDF, that will be a tough question. Fine. So I have covered everything that is required to solve the problems. Now let us attack. If they have given message as some other signal, yes, go with this basics. Signal power you find it separately, and quantization noise power we know we have the procedures to find quantization noise power for all cases. Substitute that and find it. Here also we have done the same thing. Okay, any complicated question, remember that we know the basic procedure. You have to follow that basic procedure. If there is any complication in the question, go from the basics. Right, let us start. I'll wait for 2 minutes for every question, and after that I'll solve. You can start. A signal of bandwidth 4 kHz is sampled at 25% higher than Nyquist rate and then encoded using a 8-bit PCM system. Find the sampling rate and bit rate of PCM system. Very simple question. I don't want to wait for a longer duration here. Okay, so let me do it because there are many more questions that we have to cover in this class. So what did they give us about sampling rate? It is 25%. I'll do it in a more easy manner. If anybody has a confusion about 25% higher than Nyquist rate, how to deal with that, I'll deal it in a very easy manner. 25% higher than Nyquist rate. 25% higher than Nyquist rate means original is 100%. On top of 100%, 25% extra, which means 125% of Nyquist rate. Whenever you want to change percentage into normal scale, Without converting into normal scale, we can't do calculations. So percent means per every 100. So let's convert percentage into normal scale. Whenever you want to convert percentage into normal scale, just divide with 100. Any confusion with this percentage higher kind of things, just do it like this. It will be very easy. So it is equal to 1.25 times. Once you understand this, next time onwards, once you see the percentage, you can understand that it's a factor of 1.25. In the previous slides also I've discussed this kind of model. Okay, wonderful. So it is 1.25 into Nyquist rate is 2 times B. So 1.25 into 2 is 2.5 into B. What is B? 4 kilohertz. 4 kilo into 2.5 is 10 kilo. You can say hertz or samples per second. Sampling frequency is 10 kilohertz. Sampling rate is 10 kilo samples per second. And what about the bit rate? Very simple. Bit rate is NFS. N is how much? 8-bit PCM system, so N is 8 into 10 kilo. How much is that? 8 kilo bits per second. Is that okay? It's an easy question. Guys, if you have not subscribed to the channel, please subscribe to the channel, and if you're liking what I'm teaching, please like. Press the like button, and let's continue with the next question. I'll wait for 1 minute, only 1 minute, because it should be an easy question, that's why. It is an easy question. I'll wait only for 1 minute. Come on, make it fast. Okay, fine. Let me start solving it. Right, so they're saying that it is sinusoidal signal. Sinusoidal signal means we have a comfort with that. Bandwidth is given, B is given. So they're sampling at Nyquist rate. The sampling rate is same as Nyquist rate, it seems. Sampling rate is Nyquist rate, which is 2B. 2B is how much? 8 kilo. Sampling frequency is 8 kilohertz, and then encoded using 8-bit PCM system. So small n is 8. So if the signal takes voltages from -8 to +8, so m of t takes voltages from -8 to +8. So that is the given data. Now let us quickly calculate everything. Find the step size. So step size is voltage swing. How much is the voltage swing? Highest voltage minus lowest voltage, which is 16 volts is the voltage swing. Voltage swing means the range of voltages possible for the message, which is 16 volts, divided by voltage swing divided by 2 power n, which is 2 power 8. So which is 1 by 16. Delta is 1 by 16. Okay, wonderful. What is the maximum quantization error? We know it's very simple stuff. It is half of the step size. The maximum error possible is half of the step size, which is 1 by 32 volts. Next, SQNR. Do we need to calculate from the starting? Not required, no. The message is given as sinusoidal. SQNR formula we have for a sinusoidal message, and that is 6n plus 1.8. Generally, SQNR is expected in dB scale, okay? So n you can substitute 8 here. It is 49.8 dB. That is the answer. Is that okay? Fine. Next one. Come on. Very good question. Wonderful question. If you can understand the question clearly, it will be an easy question. But very good question. My favorite question, you can say. A sinusoidal message signal. So they're saying that message is sinusoidal, which means you can assume that it is something like AM cos omega mt or AM sin omega mt kind of signal to an n-bit PCM system. The maximum quantization error, what are they saying about that? We know maximum quantization error is equal to delta by 2, correct? It is delta by 2. And what they're saying is quantization error should be less than or equal to 0.1% of peak signal amplitude, peak amplitude of the signal. What is the peak amplitude of the signal? They said that it is sinusoidal signal. They did not give any peak amplitude, but okay, we have assumed it as sinusoidal signal. We have written like this. Since we have assumed it as AM, let's write it as AM. Whatever is the peak signal amplitude, you can have a different assumption. B cos omega mt you can find. Then you can write B here. Fine. So delta by 2 is less than or equal to 0.1%, percentage into normal scale. Just divide with 100, it will get converted into normal scale. Percent. Whenever you are converting percentage to normal scale, just divide with 100, it will get converted to normal scale. And how about this one? Delta by 2. Can we change this one? Delta by 2. Delta also we have a formula, no? Voltage swing divided by 2 power n. What is voltage swing in this case? It is 2 AM. 2 AM divided by 2 to the power of n divided by 2. Because we want delta by 2, no? This is delta and this is 2. Right. AM gets cancelled and this 2 and 2 gets cancelled. So 0.1, if you bring it to the numerator, it becomes 10. So it becomes 1000 here. So 2 power n onto the other side and 1000 into this side, 2 power n greater than this 0.1 with 100 together, it will become 1 by 1000. So it becomes something like this. So 2 power n is greater than or equal to 1000. It means n should be greater than or equal to log 1000 to the base 2. So which is, we know 1024. 1024 means it can be written as 2 power 10, right? 2 power 10. So but it is it's not 1024, it's less than that, which means it is somewhere around, I don't know the exact number, but it is somewhere around 9.9 or something like that. But can we choose n as a 9.9? It's not possible, right? Because number of bits should be always an integer. What is the closest integer that we can choose? The best possible value of n that we can take is n is 10. We can't take 9.9. So should we take 9? No, we can't take 9, because if you take 9, n value is not greater than, it should be greater than or equal to 9.9 for this to happen. For the condition given in the question to happen, n should be greater than 9.9. So the only way, the closest integer possible is 10. So if you take n11 also, that is also fine, but the best value of n possible is 10. Okay, right, wonderful. Next question. This is a very good question. Small trick is there, small conceptual understanding should be there. Carefully you have to understand things. A PCM system is designed for signals taking voltages from -4 to +4. Quantizer. When you are designing the quantizer, whatever signal you give here, voltage swing of x is very important. Voltage swing of x is important. Okay, and one more thing, once you design a quantizer, based on the input signal, are we going to change the quantizer characteristics? That's not possible. Once we design the quantizer, we are going to design the quantizer keeping some things in mind. Okay, I am assuming that, okay, so and so signals will be applied. Okay, that might be the range of voltages possible for that signal. With that idea, I'll design a quantizer. Once we design a quantizer, whatever is the input, it doesn't matter. Quantizer characteristics will remain same. Once the quantizer is designed, we can't change the characteristics of the quantizer dynamically. Quantizer characteristics are fixed. Once designed, it's fixed. We can't change it. Okay. When you're designing, you're going to assume something about the voltage swing. Na? That is what they're giving here. A PCM system is designed for signals taking voltages from -4 to +4. The assumption is when you're designing a quantizer, you should have an idea of voltage swing. And what is the idea they are having about voltage swing? Okay, from -4 to +4. Signals will take -4 to +4. Okay, based on that, I'll design. But if they give us a different signal, the signal without having that swing, even then I can't do anything about it. Quantizer characteristics will remain the same. Okay, right. So question here is, quantizer is designed with a different voltage swing and the input signal is given with a different voltage swing. Say this one, 2 cos, which means the swing of the signal, this signal is 4 volts, -2 to +2. Voltage swing of the signal applied and voltage swing with which quantizer is designed, they are different. That is the trick in this question. But generally what happens is, whatever is the voltage swing with which quantizer is designed, generally those kind of signals only will be applied. That is the general case. But they are trying to test us with the core concept. Okay, so how good is our concept will be tested in this question, right? So what if the signal given is having a different voltage swing than the quantizer design? So once the quantizer is designed, its characteristics will not change. Whatever input output characteristics were plotted in the previous slides, that will not change. For any signal you apply, once the characteristics are designed, it's fixed, right? So since the voltage swing is fixed, once the quantizer is designed, voltage swing is fixed. If the voltage swing is fixed, what else is fixed? Delta is also fixed, na? Because delta is dependent on voltage swing. What is voltage swing divided by 2 power n? And how much is the voltage swing in this problem? It is 8 divided by 2 power. Okay, they are saying only PCM system. They are not giving any information. Okay, I think they should give bits information, right? Let me say it is 8 bits only. Okay, 8 bits. Bits, without bits we can't solve it. So 2 power 8. It is 1 by 2 power 5, which is 1 by 32. Step size is there, step size is fixed. Okay. Okay, so how about SQNR? If you want SQNR, since the problem is different, when we found SQNR, that formula 6n plus 1.8, in that the signal swing and the swing of the quantizer, the swing with which quantizer is designed, both are same. Only under that assumption we get 6n plus 1.8. Here in this problem, the problem is slightly different from the regular questions. Whenever the question is slightly different from the original questions or the basic questions that we have dealt with, then you have to be careful. Go from the basics. So we have to find SQNR, go from the basics. So it is signal power divided by quantization noise power. And signal power is how much? Signal power is, signal is given. It is 2 square by 2 is the signal power. It's not 4 square by 2 because the signal given is different. Okay, next, quantization noise power. Quantization noise power is designed according to that voltage swing, -4 to +4, which means we're going to this step size. And we know, because it is a sinusoidal signal, for sinusoidal signals we can assume quantization error is having a uniform PDF. If quantization error is having a uniform PDF, we know what is quantization noise power. It is del square by 12. We know that much. It is del square divided by 12. Quantization noise power does not change. So it is 2 square by 2 is 2 divided by del square by 12. What is del value? 1 by 32 or 1 by 2 power 5 you can write. Whole square divided by 12, which is equal to 2. 2 power 5 whole square is 2 power 10. 2 power 10 comes to the numerator divided by 12. So sorry, this 12 also into the numerator, no? This 12 also into the numerator. This is equal to 12 into 2 power 11. You can write it as 3 into 4 means it is 2 power 13, right? 2 power 13. So if you convert this into dB scale, so can you convert this into dB scale and tell me? So you can apply 10 log to this and find it. You can apply 10 log to this and apply. So it will become 13 3 is 39 dB because of that, and log 3 is somewhere around 4 dB, somewhere around 43, approximately around 43 dB you get. This is not the exact answer, you can find it at somewhere around 42 43 dB, somewhere around that number you'll get. You can use calculator to find it. Okay, right, next question. So here for this question I have framed 3 questions. So let us quickly answer them. First question is very easy. A signal of bandwidth 4 kHz is sampled at 50% higher than Nyquist rate. Fs is equal to 50% higher means it's 1.5 times of Nyquist rate, which is equal to 1.5 times of 2b, and b is 4 kHz, which is 3 4 so 12 kilohertz or 12 kilo samples per second you can say, and then encoded using an 8-bit PCM system. If the signal takes voltages from 0 to 16 with uniform probability, input signals PDF is also given. It is given as uniform PDF. If it is uniform PDF also, we know something about quantization noise power. We can easily calculate it, right? Right. Find the sampling rate and bit rate. Sampling rate is done, and bit rate also is very easy. It is NFS. N is given as 8. 12 8s are 96. kilobits per second. It's an easy question. Let's move on to the next question. That is also easy question. Step size delta, how much is that? Step size is voltage swing divided by 2 to the power of n. Voltage swing is 16 divided by 2 to the power of n is 8. So which is 1 by 16. And maximum quantization error is half of step size, which is 1 by 32. So why are you giving such easy questions? No, actually my intention was to give this question. For the same data, this is the question that I wanted to give you. So I just wanted to give you some practice of the previous questions also. Okay, now let us find the quantization noise power. Quantization noise power, is it easy or difficult in this problem? If you remember the data that I have told you, or the whatever content I have told you in this class, it's very easy to find the quantization noise power. Or you can go with the basics also, expectation of QE square. And if you want to find expectation of QE square, if you know the PDF of QE, we can find it. Because the signal is having uniform PDF. Signal is having uniform PDF. Because signal is having uniform PDF. Signal is having uniform PDF means quantization error also will have uniform PDF. Because they are having linear relation. X and QE are having linear relation. So quantization noise power, if QE is uniform, we know the answer for quantization noise power, which is del square by 12. Right? And SQNR. How about SQNR? That we don't know. We have not calculated for when message signal is uniform. Whatever we have calculated, 6n plus 1.8, that is when message signal is sinusoidal. When message signal is sinusoidal and quantization error is having uniform, in that case 6 it is 6n plus 1.8. But in this case we don't know. Let us calculate. But we are clear with quantization noise power because quantization error is having uniform PDF. So it is signal power divided by quantization noise power. And what is signal power? Signal is taking voltages from 0 to 16, right? 0 to 16, what is the height? It is 1 by 16 as a function of x, fx of x. This is the PDF of x. So if you want signal power, what you should do is expectation of x square. That is what you should do. Divided by quantization noise power is del square by 12. And it is integration of x square into fx of x dx divided by del. How much is the del value? Previous slide we have calculated, I think. Del is equal to voltage swing is 16 divided by 2 to the power of 8. It is 1 by 2 to the power of 4. 1 by 2 to the power of 4 whole square divided by 2. So which is equal to integration of x square into height is 1 by 16 dx, limits from 0 to 16. So it is 1 by 16 outside, x cube by 3, limits from 0 to 16 divided by this is 1 by 2 power 5, 1 by 2 power 8 to power 9. This is 1 by 2 power 9. So you can substitute that and find the final answer. It is 1 by 16 into 3, and this 2 power 9 into the numerator into 16 cube minus 0 cube, which is 16 cube. So this is equal to 116, we can cancel here. So this becomes 2 power 9 into 16 square. 16 square is 2 power 4 whole square, which is 2 power 8 divided by 3. So 2 power 9, 2 power 4 whole square is 2 power 8. Yeah, 2 power 17 divided by 3. So you can calculate this. It is 17 threes. Yeah, it should be somewhere around 17, around 50 dB or something like that. Sorry, 48 dB. Okay, it's fine. You can calculate this. You'll get the answer. Convert this into logarithmic scale. If there are any calculation mistakes, be cautious. I might have made some calculation mistake. I'm not sure, but I think whatever I've done, I believe it is correct. Because this is a complicated calculation, I might have missed something or the other. But this is the procedure. Right, wonderful. Next one, I think one last question, I think. Wonderful question. So this is the tricky question that can be given. Signal takes voltages from 0 to 8 volts with the distribution as shown in the figure. This is the distribution given. Signal is X, and this is the PDF of the signal. This is the PDF of the signal. It is quantized using a 2-bit uniform quantizer. Draw the quantizer characteristics. First question is draw the quantizer characteristics. If you want to draw the quantizer characteristics, the first thing that you need to know is step size. What is the step size? It is voltage swing divided by 2 power n. What is the voltage swing here? 8 volts, because the signal takes voltage from 0 to 8, divided by 2 power n, which is 2 power 2, which is 2 volts. Step size is 2 volts. So let us plot the characteristics. So starting voltage of the signal is 0 and the highest voltage of the signal is 8. Since the step size is 2 volts, let's divide the regions into 2 volts each. So totally 4 regions we get, because there are 4 quantization levels possible, because there are 2 bits. So 0, 2 volts, 4 volts, 6 volts. Okay. Right, now let us plot the quantizer characteristics. What is the quantization level for this region? 0 to 2 volts. Midpoint of 0 to 2 is 1. So 1 will be the quantization level for this region. And from 2 to 4, quantization level will be 3. And for 4 to 6, quantization level will be midpoint of this, which is 5. And from 6 to 8, the midpoint of that is 7. That will be the quantization level. So this is 1, 3, 5 and 7. So this is the quantizer characteristics. Let's move on to the next one. Let's move on to the next question. The same data. I have given you one more question. Right. See this one. Find the quantization noise power and SQNR of the quantizer. This is the important question. The reason I have given you this question is for this question, because the PDF is not uniform. So this is constant in this region and constant in this region. No. Uniform means whatever voltages it takes, it should be with equal probability. Here from 0 to 4 volts, it is taking with some probability. 0 to 4 volts, it is taking with equal probability. 4 to 8, it is taking with some other probability, but for these voltages, 4 to 8, it is taking with equal probability. This is not called as uniform probability density function. It should be some rectangular shape. It should be having a rectangular shape. So x as a function of PDF of x is given. PDF of x is given. Using this, how to find quantization noise power? Because x is non-uniform. For this only we have spent in the previous slides a lot of time. I told you that this is the trickiest question possible, but I have told you the procedure to do it. Right. So let's find it. So how to find quantization noise power? It's not straightforward. It's not straightforward. We have to be careful because this is non-uniform. It's not rectangular PDF. So we have to be careful. So quantization noise power is equal to expectation of QE square, which we can write as expectation of x minus y whole square. But y is random, x is also random. Since x is not having uniform PDF, QE also will not have uniform PDF. We have to mind this. QE also will not have uniform PDF. So we have to be careful. So since QE is not having uniform PDF, we can't directly find expectation of QE square as del square by 12. We have to find it with the basic procedure, and this is the basic procedure. And how do we do further? Expectation of x minus y whole square, what we can do is, we will find this for each quantization region, because for each quantization region, y will be constant. That is the technique we have discussed in the previous slides. So if you are getting any small slight confusion in this, go half an hour back in this class. There I have discussed very clearly what should be done. So the same thing we do for each quantization region. How many regions are there? In this problem, there are 4 regions. We'll do that expectation of x minus y whole square for all these 4 regions. In this region, what is the quantization error? It is x minus y, but y value is 1 here, x minus 1. And the second region, what is the quantization error relation? It is x minus y, y is 3 here. And in this region, it is quantization error is x minus 5. And in this region, what is quantization error? It is x minus 7. And in this region, What is the quantization noise bar? Only for this region, this quantization noise bar is expectation of QE square, which is x minus 1 whole square. And for this region, quantization noise bar, only for this region, quantization noise bar is expectation of x minus 3 whole square. And for this region, x minus 5 whole square and x minus 7 whole square. Okay, that is what I'm doing here. For different regions, we do it differently. X minus 1 whole square plus expectation of x minus 3 whole square plus x minus 5 whole square plus x minus 7 whole square. That's it. So let's solve it. I think till this step you have understood. I have stopped. In the previous explanation also, I told you that you have to do it this way. Okay, next step, you can do it the way I am doing it here. The same way you can proceed for other shaped PDFs also. Expectation of x minus 1 whole square, only one random variable is involved. From this step to this step, this is the crucial part. You should understand why we have done what we have done from this step to this step. That you have to understand very clearly. And you should also understand why we have done it. So this is very easy to simplify. This is very easy to find out because only one random variable is involved. So we can write as x minus 1 whole square into fx of x dx. Similarly, plus integration of x minus 3 whole square into fx of x dx. Similarly for this and for this also, plus this and plus this, which is equal to integration of x minus 1 whole square. And what is the equation of fx of x? What is the equation of fx of x? We know the equation, that is we are having equation here. And what is that? It is 2a. And how much is a? A is not given here. So we can find what is a value. Total area should be 1. That is the funda. Okay. Let's divide this into two rectangles. So first rectangle, the bottom rectangle is 8, height is 8, and width is 8 and height is a. 8a is the rectangle, this rectangle's area. Plus what is this rectangle's area? Width is 4 and height is a. This 4a. This should be 1. So 12a should be 1. A should be 1 by 12. So 2a means this is 1 by 6 and this is 1 by 12. Right. We know what is the equation of fx of x. It is 1 by 6 for 0 less than x less than 4. And it is equal to 1 by 12 for 4 less than x less than 8. So fx of x. How much is fx of x? For the first quantization region, x minus 1 whole square equation is valid only from 0 to 2. And this equation is valid only from 2 to 4. Because in place of y, we can substitute 3. So this is valid only for values of x from 0 to 2. Because only for values of x from 0 to 2, y will become 1. Similarly, values of y will become 3 only for values of x between 2 to 4. Similarly here and here. Okay, you can calculate this expectation of. So what is the equation of PDF from 0 to 2? From 0 to 2, the equation of PDF is 1 by 6. From 0 to 2. And the equation of this, equation of the PDF in the region from 2 to 4. From 2 to 4 is also 1 by 6. If it is some other PDF, you will have some other equation here, maybe more complicated equation. That equation you substitute here. Once you substitute, the remaining part is only simple mathematics, nothing more than that. Similarly for these two also you can write. Similarly you can calculate. You can do the calculation. So it is going to take some time and my board space also will not be sufficient. So it's a simple mathematics, you can do it. Whatever PDF they might give, write the equation for the PDF in different regions and just substitute that in this. You'll get quantization noise power. And one more thing, if once you know quantization noise power, if you want to find SQNR, there are two components, signal power and quantization noise power. So once you find quantization noise power, you can substitute in this. In this, one more thing we want is signal power. So signal power is also not straightforward here. Signal power also we have to find separately. Signal power is equal to expectation of x square, which is equal to integration of x square into fx of x dx. So we are having the equation for fx of x. Let us substitute that. For 0 to 4, we are having a certain equation, which is 1 by 6. And for 4 to 8, we are having a different equation, which is 1 by 12. Just simplify this. You'll get the signal power. Very simple to find the signal power. Right? So with this we're done with this problem. You might take a little bit more time, 1 or 2 more minutes to get the final answer, find it. But the procedure, that is what is important. Whatever procedure is required and why we are doing in this procedure only, that I have explained in the previous slide and in this slide also. Try to understand that carefully. Once you understand that, any problem given in quantization, we can solve it very easily. Right, that's it. So we are done with, I've covered almost all the possible questions from PCM system. It may not be 100% of questions possible from PCM, but I've covered most of it within the limited time that I have for PCM. I have yesterday 1 class and today 1 class, only 2 hours. Within that 2 hours, I have covered a lot of stuff, much more than I have thought of. Right. So if you guys are more active, I can share more content also. So I want to see you people to become more active. So that will give me more motivation to share more content. And this is the homework questions. I have covered all models in this I have given 4 questions. So post the answers in the comment section, the same as the yesterday's class. So there are 4 questions I have given. So 4th question is a tricky one. So if anybody can solve it and post the answer in the comment section. Let's see how good is your understanding. Okay. Right, whoever answers correctly, I'll take a screenshot of their answers and I'll share it in the tomorrow's class. First thing I'll do is share it in tomorrow's class, first in the starting of the class. So that's it guys from my side. So take care, good night, subscribe if you have not subscribed, and like the session if you liked what I taught. Okay, that's it guys, thank you. We'll meet tomorrow, same time.